It's nighttime, so good evening, Americas. Good morning, Asia. Good early morning to Europe, Africa. I think good afternoon to Australia, New Zealand, and good morning all the time. Well, not really all the time, but 24/7 sunlight in Antarctica. And I guess good night all the time to the Arctics. The Arctic Circle is in darkness. Not for too long, not for too much longer. Spring is coming. Spring is coming in the northern hemisphere soon here. The days will be longer. We can't wait in Boston for daylight savings and days being longer. I know nobody likes daylight savings, but in Boston, in the northeast of America, what that means is that the days will hopefully be a little longer. It gives us some hope, gives us the will to live and keep on going in these less bright days. Well, it has been very sunny ever since our last snowstorm. We got a snowstorm, then we got another one and another one, and then it's been sunny for a few days, so we are thankful about that. Thank you for being here, everybody. Thank you, thank you, thank you. Thank you, thank you, thank you. Thank you, thank you, thank you. We will talk about superstring theory today. So we are talking about this, and remember that we have actually talked about this in the past, especially if you're interested in this topic and if you're interested in, Goku says, I know Korean. Very good job. Very good job, Goku. If you're interested in Einstein's work, grand unified theory discussion, and sort of the evolution of modern physics as it evolved in the 20th century, that is in the 1900s. So any year that is with a 1900, basically 1905, 1920s, all of that time was spent doing a lot of really good work and in advancing our frontiers in different types of physics. So sometimes in certain universities and colleges, you will see, like in undergrad physics, that is, in undergrad majors, there's a class that's sometimes offered, which is called modern physics. And it's sort of a mix of some introduction to like quantum, maybe a little bit of special relativity. And pretty much what that class kind of entails is mostly the happenings of the 20th century. So I keep mentioning the 20th century physics on this channel because it's a very important century. A lot of very cool things happened where our understanding of physics and what we sort of do even really changed and progressed. Whereas ever since that time, so ever since sort of the later 1900s, so like 1980s and onwards, even now, where we're more focused is possibly experimentation, measurement, observation, and trying to make the measurements and do the observations and perform the experiments that will confirm a lot of the stuff that was discovered, invented, and the insights that were gained in the 1900s, especially in the early 1900s, the 1920s, the 1930s. And remember, of course, that there were the two world wars during the 1900s, which also affected and influenced the type of science that happened. In spite of those wars, a lot of really good science, and in some cases, maybe even because of the wars, certain developments were furthered in the 1900s. I'm not saying that wars were a good thing. Not good at all. But a lot of really good advancements happened in the 1900s that we must understand. And once we kind of cover all that, then we're ready for the more recent stuff. So I'm saying all of this, but I've actually already covered all of this as a discussion in the past lives. So if you're interested, I'm just mentioning that if you're interested in these modern physics, and by that, what I mean is the 20th century physics type of science and physics, then feel free to go find the live streams that are a little bit older at this time. Like I would say a few months back in October and November, I was covering almost every live was pretty much a topic from the 20th century physics work. So if you're interested, then definitely go and watch those or rewatch or listen to it, or you can do some other thing and Just listen to it. And we actually covered the topics from this book quite extensively during those lives. So that's another thing I wanted to mention as well, is that we covered the topics a lot during that time. And some of you joined the channel since that time. So you might not have caught these topics that we talked about during that time, which is like around October and November of 2024. So, but all of the lives, all of the video uploads from those lives are on the channel under the live tab. So anytime you're interested, anytime you want to go look, you should feel free to do that. And especially because we're going to touch upon superstring theory today, that's also why I'm mentioning all of this, is because superstring theory took some time to develop, and it is where it is now. And the backdrop of all these things that happened in the 1900s is very important to understanding why superstring theory was needed and what is the motivation and what is the great significance of that work. And if you kind of follow our journey, like we were following that 20th century physics, almost like a history of science kind of way, we followed that discussion, then you will really start to understand what the importance is, why, where is it coming from, okay? So that's why I'm mentioning all of that. So I'm gonna give you a summary of sort of what we covered at that time and sort of the motivation for superstring theory before I get into the part of the book that talks about superstring theory, because, you know, this book, we covered this whole book already. So I'm not going to cover the whole book today for your benefit. I will just kind of summarize the history that led to needing superstring theory. And what it is really is, it's a great candidate for the grand unification theory. And why this grand unification theory was something of interest at all is another historically interesting topic. So we will talk about all this. I'm going to share the live and we will talk about all this. Welcome to the live. Thank you for joining. Please do like the live. And thank you for being here. And yes, welcome, welcome. Hi, Batman. Hi, Goku. Thank you. Okay. I'm just going to say we are live on the channel, okay? So this topic, by the way, is very interesting to me. I love the 20th century physics, because to me, it's everything that we need to know in order to understand why we are where we are right now. So it's almost like by understanding the history of science from the 20th century, we understand why we are where we are at this exact point in time. And what types of research are the current research topics, why those are being researched right now, why those are unknowns right now. All of that is built up by discussing the 20th century physics, okay? So once again, thank you for being here. Hi, Lama. Lama says, hi, I'm back. How are you? Hello, I'm back. I'm gonna go troll. I don't feel like learning. Okay. Thank you so much for joining. What day is it? Is it Monday? Okay. Thank you. Thank you for liking the live. Okay, so we will get started. Okay, bye. Thank you so much for joining. If you're joining, Harper, hello. Let me take a sip. Actually, let me refill this with water. I'll be right back. And then we will talk about superstring theory. Actually, you know what? Let me give you a little bit of a background first. So in the 20th century physics that we covered, we saw In 1905, remember, was the year where many, many important things happened. Einstein released 4 amazing papers in that year. And a big, big, big contribution by Einstein, of course, was special theory of relativity. And so with that, we got the relative nature of space-time, energy-mass equivalence. He also worked on photoelectric effect and Brownian motion. So that year, 1905, is an amazing year. And of course, remember that photoelectric effect is giving us what sometimes we call the old quantum theory, or the sort of original quantum theory, because it gives us the particle nature of light. E&M, electricity and magnetism, and special theory of relativity is basically the updated theory for understanding light, electric and magnetic fields. Oscillating electric and magnetic fields is light. So, hi, Andrew. Thank you. Thank you for subscribing. I gotta go. I was born 1995. Okay, well, that's not too recent. I was sick on Saturday, so I've been here much. That's okay. Please do like the live. Andrew and Harper, if you could like the live, that would be amazing. Thank you so much. So, in 1905, we got all these great contributions from Einstein. And around that time and before, of course, we saw a lot of developments in E&M, electricity and magnetism theories, and then special theory of relativity gave us the even more updated theory for light. But then on the other hand, we also got the particle nature of light with the photoelectric effect. So this whole wave-particle duality of light also led some people, influenced them to think about the wave-particle nature of matter as well. So we talked about quantum mechanics and how it kind of developed in parallel, along with sort of the more classical type of physics or the relativity type of physics, because of course Einstein worked on special theory of relativity and then also worked on general theory of relativity. And along with all of this work, developed something quite interesting, bizarre, very different, very unique, and very new, which is of course quantum mechanics. And we got the wave nature of matter. So this whole development was extremely interesting, extremely amazing, and extremely intriguing. And we have covered the history of this in detail in those lives that I mentioned from October and November of last year. So if you're interested, you should definitely tune into those and listen to those. And I think you'd find them to be very entertaining because we got into all of the nitty-gritty and we had very good discussions. Now, because quantum mechanics was bizarre, there were people who didn't really like it. In fact, there were people who had contributed to quantum mechanics who didn't like it, such as Schrödinger. He wrote down the wave equation for a particle, and later on, people realized that this is actually a probabilistic way of writing down the wave equation of a particle, and you actually get a probabilistic answer from that. So classical mechanics is deterministic. Everything that people kind of knew so far was deterministic. It's like when you write down the position of something as a function of time, it's predictive, you know it. I can tell you where the moon will be in like 20 years, that type of thing. People were used to, like classical mechanics supported the old sciences. Astronomy is really old, right? We've been doing astronomy for forever. And classical mechanics gave us a way to understand and postulate, encapsulate, describe, explain astronomy, astrophysics, all those types of things in such a good way, in such a deterministic way. All the laws, the Newtonian mechanics, the Kepler laws, all of that is deterministic. It is, can I see your cat? Yes, in a minute I will show you Baji. He's right here, but I don't want to move the camera right now. It was very good at giving people answers to things in a sort of we get it, we understand it, we can predict it kind of way. And all those laws, the planetary motion laws, the, in general motion laws, everything kind of, it was very deterministic. So when we started to work on quantum mechanics and we developed quantum mechanics and we said that now when you write down the equation for a particle, its position as a function of time, you can't actually know it deterministically. You can only come up with a probabilistic answer for that. And uncertainty is a fundamental aspect of nature. It's not that we're making errors in measurement. At those small scales in quantum mechanics, you have uncertainty and things will be probabilistic. So even some of the people who contributed to quantum mechanics actually were very uncomfortable with it, and they were not very happy with the fact that this was so different and so bizarre. And of course, there were some actual bizarre outcomes as well. And quantum mechanics could have been dead had it not been for the fact that it was very successful. Experimentally, it was very successful. It was able to explain and give us hydrogen atom and understanding of it, and all those, the step-by-step, the quanta of jumps in the hydrogen atom energy states and things like that. Like all of those things, like Niels Bohr, we talked about him, all of the contributions from quantum mechanics experts that we got were experimentally proved and experimentally successful. And physics is an experimental science. So even if people were uncomfortable, they had to kind of accept it eventually. But that does not mean that people were very excited about the fact that quantum mechanics was so weird to them. And of course, though, that quantum mechanics is successful because now we have even more quantum mechanics and we have particle physics, which has come about as a result of quantum mechanics. Because quantum mechanics is successful, there were people who could keep working on it and get funding and discover new particles like every day. So the 1900s, I almost said 19th century, but no, it's the 20th century and 1900s, we saw the discovery of so many particles, like the fundamental particles, subatomic particles. Like we were discovering these particles and we were able to come up with sort of the theory of these things, the theory of the small, which is quantum mechanics, and take it forward. So all of that is to say that quantum mechanics is very successful and it's still going on, and we have particle physics and we have a bunch of particles and we have the standard model of particles, and we even think about beyond standard model of particles as well, because the standard model doesn't quite capture everything, but the point is that it has kept going. It has not died, right? So now, having said all of that, to give you some idea, let me now also say that even though quantum mechanics was very successful, it still belonged to this other camp of physicists who worked on it. There was still the first camp, or I don't know which camp is first or which is second, but there were two camps. One camp was I'll use this one for quantum. One camp was the quantum mechanics camp, and the other camp was people who were working on more classical things, relativity. Einstein was heading the efforts to come up with what we call, or what they called, grand unification theory, GUT. So we have some live streams actually about that as well, and we have discussed it in more detail in those live streams. So in the past, we've done this in quite a bit. But basically, what was the big motivation for grand unification theory? They didn't really like the bizarreness of quantum. Okay, they didn't really like it. So they wanted to come up with a more general theory which would capture general relativity, quantum, E&M, gravitation. Everything would be, hello Wade, howdy from Texas, very nice, hello. They wanted a more general theory that would explain gravitation. It would encompass all of quantum mechanics because they don't really like quantum. So if there is a more general theory that can explain what we see in quantum mechanics, then they would be happier because they're not a fan of some of the effects, shall we say, of quantum mechanics. They didn't like it. So that's why it was very hugely motivated. They were very, very, very motivated to come up with the grand unification theory because they're actually trying to come up with an alternative or a second, different, bigger, more broad theory, or the GUT, grand unification theory, which will hopefully replace quantum mechanics. That was the motivation. Hey Siri, can you go away? Okay. Siri is Hi Reese. Oh my god. Siri is being crazy. Sorry about that. I have my iPad open so I can see the comments over here and whatever. So I love this topic, so I can talk endlessly about it, but I wanted to be as coherent as I can. So I want to stress that quantum mechanics was very successful and people were budding scientists and winning Nobel Prizes by doing quantum mechanics and particle physics. But that does not mean that it was not contested. That does not mean that there were people who were not unhappy with it. There were people who were unhappy with it. There were very famous people who were very unhappy with it. And it was difficult for them to accept certain parts of quantum mechanics. So when that happens, what would you do? If you wanted to control and solve this issue, what would you do? You would want to work on something else, some alternative theory, some bigger theory that can encompass quantum mechanics, that also explains gravitation and can basically, you get general relativity out, and that can also explain light and E&M and everything. So what is the theory of everything? What is that one bigger, broader theory that explains everything? And this is what people were working on. And this is what Einstein was leading the efforts for. And we talked about this from this book earlier, and we will touch upon it again today. And superstring theory is one of the candidates for that GUT, grand unification theory. So this is why this was the long summary and motivation introduction for why we even talk about superstring theory, why, where does it come from, what is the motivation. Before we go into what it is and get into more details of it, and I also need to find more references, more books that will explain it, because I'm not an expert on superstring theory. People do ask about it, so I'm gonna at least address it and cover it today. But I definitely need more materials and more books on it so that I can tackle it more broadly and more better, more good-like. So, but this book that we read back in those days, in the October-November lives, very much gives us the history that will explain the motivation for superstring theory. So hopefully that makes sense, and hopefully you can kind of follow now what the motivation was, and that's what we'll talk about. I need to fill up my water. I'll be right back. Thank you so much for being here. And now we will get into it. I just wanted to give you the big, long introduction and summary first, so you understand the premise. And of course, it didn't just happen overnight. Hi, Reese. Yeah, no, I don't see anybody yet. I don't see the usual people too much yet. Excuse me. I need some more water. I don't see Doro. I don't see Grimmy. Superstring theory is equal to why the string on my sweater can be pulled out like 6 feet before it breaks. Hello, Wade. Hello, Reese. Hello, everybody. Thank you for being here. Someone could tag the other people who are missing right now in the live, and that way we can maybe see them. I'm gonna get water. Thank you so much for being here. We will now start with superstring theory from this book that we have been referencing. Yay! Okay. Okay, so here I am. Can you please like the live? Can we get 20 likes? Reese, this is my new phone. Can you tell? Do you see any differences? I do have one extra light on as well. I have an extra light on, and this is my new phone that arrived today. It's my new refurbished phone. It's my new old phone because I don't buy new phones. So it's an iPhone 12. Finally got a phone? Yeah. Camera quality looks good. Thank you. Okay. Android. Sure. Sure. We'll support you. Okay. Physicists. So we're going to read a little bit from this book to give you some idea, okay? I don't know how I'm going to hold it. Maybe like this, maybe like that. No, I don't want to block the light. Actually, let me go like this. Physicists today have formulated the most advanced version of quantum physics embodied in something called the Standard Model. So I mentioned about the Standard Model, how that has come about from particle as a formalization of particle physics, basically. So that's what that is. So physicists today have formulated the most advanced version of quantum physics embodied in something called a Standard Model, which can explain subatomic experimental data. It is in some sense the most successful theory in nature, able to describe the properties of three, the electromagnetic and the weak and strong nuclear forces. So particle physics, as encapsulated, as formalized by the Standard Model, does explain E&M. So interaction of photons, for example, E&M. The weak force, that is neutrinos, Neutrinos interact through the weak force. Strong nuclear forces as well. Quarks, so protons and neutrons within the nucleus of an atom experience the strong nuclear force. So all of those are part of the Standard Model. It's part of those particles and the interactions between the particles in the Standard Model. So of the four fundamental forces, the fourth one being gravitation, three are pretty well explained in the Standard Model. As successful as the Standard Model is, there are two glaring problems with it. First, it is supremely ugly, says this author. I'm not sure that I would call it ugly because I don't like to I don't say such things, but according to a string theorist, it is ugly. Perhaps one of the ugliest theories ever proposed in science. The theory simply ties together the weak, strong, and electromagnetic forces by hand. It's like using Scotch tape to connect a whale, aardvark, and a giraffe together, and claiming that this is the supreme achievement of nature, the end product of millions of years of evolution. So it's basically saying, he's basically saying that those three things, the electromagnetic forces, strong force, weak force, I mean, the Standard Model basically, it's almost like a table of a bunch of particles and a bunch of other particles that help. So basically the Standard Model is, what is it? It's leptons, quarks, and bosons. And between those three types of particles, which is all the particle families, and we've talked about that as well in the past, we're basically explaining these particles, the way they interact. And these are the things that basically cover electromagnetism, the weak force, and the strong force. Now, as far as understanding like what these things are more in a more basic and fundamental way, like why, what is up with the strong, like what is a more general theory that would encapsulate or give us some deeper insight into the strong and the weak and the electromagnetic force, that is not really as well done by particle physics, as pointed out by this author. And that's what he means. It's kind of like, okay, it's saying, it's particle physics or Standard Model is almost like saying, here's the laundry list. Here's some particles and here's some other particles, and that tells you all the things and how they interact. And it's kind of like it's kind of trying to be as exhaustive as you can in saying these things. And saying, okay, here we go. Like, this is it. That's it. Now we understand the entire, family of particles and forces and all that. But where is the sort of deeper insight that would tie everything together? That is what is sort of missing according to the author here. Okay? Like, for example, remember when Einstein worked on special theory of relativity, he was able to tie together all the things we knew already in E&M with the deeper insight about light, about the wave nature of light. The fact that the speed of light in vacuum is a constant, all of that led to this more and more understanding, or a better, bigger, deeper understanding, more than we ever could achieve before that time. And it tied together E&M and light, right? And the nature of space-time. Then he worked on general theory of relativity, which tied together all of that, plus gravitation, right? So it's beautiful. It ties things together. It gives deeper insight. It talks about the, curvature of space-time and how gravitation bends space-time. It's gravitation in general theory of relativity is not a force anymore. It's the fabric of space-time. So it's beautiful, classical, more and more sort of insightful. It tells you sort of like it's more about understanding it deeper and getting an insight out of it. Whereas these things, the particles, are sort of like here's some things, learn it, memorize it, let's go. It's more, it's two very different approaches. Okay, so the theory simply ties together the weak, strong, and electromagnetic forces by hand. It's like using Scotch tape. We saw that. Up close, the Standard Model consists of a bewildering, motley collection of subatomic particles with strange names that do not make much sense, like quarks, Higgs bosons, Yang-Mills particles, W bosons, gluons, and neutrinos. So he's kind of talking about how there's a lot of particles. Like the Standard Model is not just one or two particles, it's a ton of particles, right? So I mentioned the three families, leptons, quarks, and bosons. Under the leptons, we have a ton of different particles. Under the quarks, we have a few different quarks. Under the bosons, we have a few different bosons. So, it's, again, it works, and it's experimentally proven, and it's got experimental success, and discovering these particles and how things work. It works. The Standard Model of particle physics is still a thing. Just because somebody finds it ugly doesn't make it go away. Okay, it's going to be a thing. It's a thing. It's progressed physics. It's given us experimental results that you can't ignore, and in fact, you need. So this person's point of view is valid in that it's not the most graceful, ties everything together and gives you a deep insight kind of story. But the fact is that you have to kind of just get over that. Until you come up with a better theory, you just have to take it, right? And that's kind of where we're headed, which is to try and get a better theory, which, by the way, is incomplete, because we're going to talk about the grand unified theory today a little bit, but it's not achieved yet. They tried, and it is still a work in progress, as far as I know. I don't believe that they achieved it, okay? Worse, the Standard Model does not mention gravity at all. So it does not. That's the other thing about the Standard Model, is that it doesn't really explain gravitation. For gravitation, we do rely still on general relativity. And if you don't care about relativity, if that's sort of not a thing for the environment you're working in, then Newtonian mechanics is just fine. And so gravitation, again, when we go to school for physics, we would learn about it in Newtonian mechanics and in general theory of relativity, if you take that. If relativity is not important for your problem, then you wouldn't even learn that. So yeah, it could be that the grand unification theory is unobtainable, but for the people who were working on it, they were still very hopeful about attaining it. And even now, I would say there is still a lot of motivation, because it's kind of like you can help out with the more and more direction of particle physics, or you can do something totally different. And this is sort of the totally different, which is to come up with a completely different, additional, broader, bigger theory that will explain everything. It is difficult, though. I'm not saying it's easy. So if one tries to graft gravity onto the Standard Model by hand, one finds that the theory blows up. It yields nonsense. All attempts for almost 50 years to graft the quantum theory and relativity together have proved fruitless. Given all its aesthetic defects, we conclude that the only thing going for the theory is that it is undeniably correct within its experimental domain. Clearly, what is needed is to go beyond the Standard Model to re-examine the unification approach of Einstein. So even this person, the author of the book, Michio Kaku, is admitting that in spite of all his issues with quantum mechanics and with particle physics, it is undeniably successful. It has undeniably yielded experimental successes and results that you can't ignore. It has progressed our understanding. So you can hate it, love it, you can't ignore it, So it is something we have to learn. It is something we have to work with, and it is something we take into account. And if, by the way, if you want to challenge it and come up with a new theory, it better explain it. It better contain particle physics, right? Because how come you don't wear your ring anymore? I mean, I wear it sometimes. I don't wear it sometimes. You know, I've not been well, so things are a little bit shifted, I guess. Still adjusting. So basically, the challenge also for grand unification theory at this point, the more quantum mechanics progresses and the more particle physics progresses and the more new particles are discovered, if you're challenging particle physics, you look a bit better. Yes, I do feel better than before. Thank you, universe. Hopefully it keeps going that way. If you're going to challenge quantum mechanics and particle physics, your new theory better explain it. You can't just challenge particle physics. You have to say that whatever theory you came up with can contain it, can explain it, can subsume it, right? It can basically swallow it and spit out more, right? It and more. Like the output of this new theory better be something that can explain everything we know so far and more, right? And that's the challenge. It's not so easy to just output everything from quantum mechanics and particle physics because there's so much that we know now within those fields that are experimentally observed, that are experimental outcomes. And so there's all those like modes, there's all these like properties of the particles, the spin, the this, the that. You have to be able to explain all of it with your grand unification theory if you're working on one. No pressure. But that shouldn't discourage you from working on one. But at the same time, keep in mind that you have to explain all of that, right? So let's see what they did with that. So after 50 years, the leading candidate for a theory of everything, one that can unify both the quantum theory and general relativity, is called superstring theory. So for the first time, I'm defining for you with the help of this book, what is superstring theory, because somebody asked about it. I don't know if that person is even here today, but here we go. In fact, it is the only game in town because all rival theories have been ruled out. So superstring theory is a candidate for the grand unification theory or the grand unified theory or GUT. Basically, it is a theory. It's not proven, but it is a theory that tries to do exactly what Einstein and the others back in the day tried to do, which is to come up with a more general, more broad, beautiful, classical, amazing theory that can contain everything and try to explain all of that within itself. Now, superstring theory, I don't know. Hi, Steven. My name has one more E, but good to see you. Superstring theory is a candidate for GUT. In fact, it is the only game in town because all rival theories have been ruled out. As physicist Steven Weinberg said, string theory has provided our first plausible candidate for a final theory. Weinberg believes that the maps that guided the ancient mariners all pointed to the existence of a fabled North Pole. Yes, hopefully we'll get into that a little bit here in a second. Thank you for asking. Hi, Harper. Weinberg believes that the maps that guided the ancient mariners all pointed to the existence of a fabled North Pole, though it would take centuries before Robert Peary actually set foot on it in 1909. Similarly, all the discoveries made in particle physics point to the existence of the North Pole of the universe, that is a unified field theory. So basically they're saying that all of the particle physics stuff that we have found are sort of part of something bigger. What is that bigger thing? What is that unified field theory that can explain all of particle physics and such? And the more particles got discovered and the more properties of those things got discovered, the more these theorists were like, there has to be something grander, something something broader and more beautiful that can explain all these particles and their properties as a part, as a subset of it. Superstring theory that can absorb all the good features of the quantum theory and relativity in a surprisingly simple way. Superstring theory is based on the idea that subatomic particles can be viewed as notes on a vibrating string. So here we go. Here's the string stuff. Superstring theory is based on the idea that subatomic particles can be viewed as notes on a vibrating string. I'm sorry if I roll my eyes because I'm not a string theorist. So some of it is a little bit, how should I put it? It's a theory. Although Einstein compared matter to wood because of all its tangled properties and seemingly chaotic nature, superstring theory reduces matter to music. Einstein, who was an excellent violinist, probably would have liked this. So it's unfortunate the grand unified theory was led by Einstein when he was living. But by the time superstring theory is coming out, Einstein has passed away. So he probably did not really see superstring theory. Yes, now you did. Thank you, Stephen. Einstein probably did not really see the end result of superstring theory and what kind of theory it sort of evolved to, because Einstein passed away. But remember, Einstein was extremely motivated to work on the grand unification theory. And so all of this progress that we saw in superstring theory it would have been lovely if Einstein was still here and seeing all of that progress happen and giving his input. But very unfortunately, we lose these great people and they're not around anymore to give us the feedback. That would have been useful, you know? At one point in the 1950s, physicists despaired of making sense of subatomic particles because new ones were being discovered all the time. Yeah. Exactly. So by the way, let me real quick answer the question that you asked. We will get into some more of the details here, but let me real quick answer. So sorry if you already answered my phone. Could you explain why string and superstring theory require 10? I think it's 11 actually, but you mean with time? Yeah, 10 I guess 11 with time. So, but double check the however many dimensions. It's however many they needed to explain what they were trying to explain. Aw. It's not the case that we need to figure out more quantum stuff. It's the case that we need to have a theory that can explain the currently known quantum stuff. We know a lot of quantum stuff. For example, the spin properties of the different quantum particles, like fermions, electrons, different spin than bosons, as an example of quantum properties of different various particles, right? So it's not the case that we need to know more quantum. Sure, we can always know more quantum and more particle. And in fact, I mean, that is going on. But it's the case that whatever the grand unification theory is, has to be able to explain what we do currently know in quantum and particle. If it cannot, then it's not a broad enough or grand enough theory that can subsume the currently known stuff. Because if particle physics is giving us something that we experimentally observe and that explains our current reality, basically, like electron, it's a part of nature. It's part of our existence. Neutrinos, we see them from the sun, you know? Like, it's not just that particle physics spewed out a bunch of particles that are not the reality. Particle physics has a bunch of particles that we see in nature. And those particles have different properties. different from each other. We discover new ones. They have new properties. That's what nature is showing us. Nature might not be showing us everything, but what nature has shown us must be subsumed and encapsulated by a grand unification theory. And if it cannot, then we won't accept it. It will be highly contested. I'm not saying that somebody should not work on a GUT, but it won't be easy because we do know a lot already that has to be explained by it. And yeah, the 11 dimensions are a part of that attempt. They came up with however many dimensions they need in order to explain some basic stuff. And because we can't do experiments with 11 dimensions because we only experience 4, string theory, in short, by the way, we will keep reading about it, but superstring theory, in short, cannot be proven. It cannot be experimentally demonstrated. And that's why it's still called superstring theory. There's no superstring experiment. And physics is an experimental science. You have to show things experimentally in order for it to be accepted as a science. And so, unfortunately for the superstring theorists, even though their theory might be more beautiful than particle physics, it remains a theory rather than an experimentally proven fact because we can't do experiments with 11 dimensions. I mean, not yet, anyway. We experience 4 dimensions, including time. It could be that we're limited. Part of the discussion is that we could be limited. We just don't experience these extra dimensions because we're limited. We just don't. It could be that we don't. But the fact remains that it's challenging. It's challenging for the theory. It's challenging for the field to accept it without proving it out. Okay? So at one point in the 1950s, physicists despaired of making sense of subatomic particles because new ones were being discovered all the time. Oppenheimer, in disgust, once said, "The Nobel Prize in Physics should be given to the physicist who does not discover a new particle this year." Because the particles were being discovered quite often. These subatomic particles were given so many strange Greek names that Enrico Fermi said, if I had known that there would be so many particles with Greek names, I would have become a botanist rather than a physicist. But in string theory, if one had a super microscope and could peer directly into an electron, one would find not a point particle, but a vibrating string. When the superstring vibrates in a different mode or note, it changes into a different subatomic particle, like a photon or a neutrino. In this picture, the subatomic particles that we see in nature can be viewed as the lowest octave of the superstring. Thus, the blizzard of subatomic particles discovered over the decades are simply notes on this superstring. So superstring comes from string. String theory is the basic, and then superstring would be all the octaves that give you the other notes to properly explain all of the different types of particles, as an example. And so, part of the issue, as you can maybe imagine, part of the big issue was the lack of beauty. The string theorists were looking for something more beautiful. They wanted a more classic, beautiful, simple, elegant theory that can explain nature. That can be like electrons, neutrinos, photons, everything string. Everything's a string. It just gives them a more elegant solution. Now, is elegance always what is needed? Is elegance the only thing that is helpful? Maybe not, right? I think a particle physicist might say that it's okay to be non-elegant sometimes if it helps you to solve a problem and to understand the diversity that is really out there, right? Like, sure, maybe you can call an electron a string and say that the neutrino or a photon is also a string. It's almost like how do you want to see this world? How do you want to see the universe? And string theory, superstring theory, could very well be a way to see this universe in a more elegant, more simple manner. But, hi Doro, hi Stephen, hi Reese, hi Combat. It could very well be a more elegant way of looking at this universe, but whether it's helpful or not may depend on the person you're talking to. Because not everyone thinks of things the same way. And the quantum people, the particle people, may very well resonate better with that particle-y way of looking at the universe, okay? So this blizzard of subatomic particles discovered over the decades are simply notes on this superstring. The laws of chemistry, which seem so confusing and arbitrary, are the melodies played out on superstrings. The universe itself is a symphony of strings, and the laws of physics are nothing but harmonies of the superstring. Superstring theory can also encompass all of Einstein's work on relativity. So that's the other thing. Superstring theory does encompass relativity. It's almost like you have to do relativity first, right? Like you start with relativity. General theory of I see Andrew has a phone now. Yes, I have a phone now. General theory of relativity already was doing a different kind of thing. It was already working with the 4 space-time, right? The 3 spatial and the 1 time, giving us 4 space-time. We were already looking into geodesics and a different way of doing the math because the usual way, Euclidean way of doing math doesn't work anymore in general theory of relativity. So remember, if you go to the lives where we talked about the math for GR, you basically have to, like, we define the metric, geodesic, the way of doing math, which will set things up so that we can write down the equations in general theory of relativity. Remember, like the Einstein tensor and the Ricci tensor, remember all that stuff. That is the mathematics that we had to set that up in order to do general theory of relativity. So you're already in a different realm. If you can do 4 space-time, why not 11 space-time, right? If you're already in a different realm, why not build on that? So basically, string theorists were like, well, we have to start with GR. We have to at least do the math in a way which allows and accepts and encompasses general theory of relativity. Like there's no 2 ways about that. You have to start there. It's something that has to build on that, right? On top of that. So, I think one of the greatest gifts of superstring theory, if you ask me, not a string theorist, I'm not a string theorist, simply just discussing the topic. The biggest thing about string theory is that these people who work on it are very good at GR. They're good at relativity. So those are the professors whose class you want to take if you want to learn general relativity. Okay, so if there's one takeaway from this discussion is that those people can know the math for GR, and not everyone can do the GR math. So you know who to ask for that, okay? So superstring theory can also encompass all of Einstein's work on relativity. As the string moves in space-time, it forces the surrounding space around it to curve, precisely as Einstein had predicted back in 1915. In fact, superstring theory is inconsistent unless it can move in a space-time consistent with general relativity. It builds on general relativity, so of course it should work, you know? As physicist Edward Witten has said, even if Einstein had never discovered the theory of general relativity, it might have been rediscovered via the string theory. Sure. Witten says string theory is extremely attractive because gravity is forced upon us. All known consistent string theories include gravity. So while gravity is impossible in quantum field theory as we've known it, it's obligatory in string theory. However, string theory makes some other quite surprising predictions. Strings can only consistently move in 10 dimensions, 1 dimension of time and 9. So maybe I was wrong. I don't know where I got the 11 dimensions. String theory makes some other quite surprising predictions. Strings can only consistently move in 10 dimensions, 1 dimension of time and 9 dimensions of space. In fact, string theory is the only theory which fixes the dimensionality of its own space-time. Like the Kaluza-Klein theory of 1921, it can unify gravity with electromagnetism by assuming that higher dimensions can vibrate, creating forces that can spread throughout 3 dimensions like light. If we add an 11th dimension, oh, this is where I got it. The M theory, that has 11 dimensions. If we add an 11th dimension, then string theory allows for the possibility of membranes vibrating in hyperspace. This is called M theory. So I thought it was 11 dimensions because the M theory has 11 dimensions. Apparently, string theory just has 10, including time. What time is it? No, I'm not a string theorist. Like the Kaluza-Klein theory of 1921, it can unify gravity with electromagnetism by assuming that higher dimensions can vibrate, creating forces that can spread throughout 3 dimensions like light. If we add an 11th dimension, then string theory allows for the possibility of membranes vibrating in hyperspace. This is called M theory, which could absorb string theory and provide new insights into the theory from the vantage point of the 11th dimension. Why would Einstein think of superstring theory if he were alive? What would Einstein think of superstring theory if he were alive today? The physicist David Gross said Einstein would have been pleased with this, at least with the goal, if not the realization. He would have liked the fact that there is an underlying geometrical principle, which unfortunately we don't really understand. The essence of Einstein's unified field theory, as we saw, was to create matter out of geometry. Gross commented on this, to build matter itself out of geometry. So basically, general theory of relativity, GR says that the curvature of space-time is due to gravitation. And then string theory is saying, like, all of that geometry, all of that needing those more dimensions and all of that geometry stuff is the broader thing, and everything will come out of that. The matter, the electron, the neutrino, all of that will come out of that. To build matter itself out of geometry, that in a sense is what string theory does, a theory of gravity in which particles of matter, as well as the other forces of nature, emerge in the same way that gravity emerges from geometry. So in GR, gravity emerges from geometry. In string theory, everything emerges from geometry. So that's the thing. And you have to really make everything emerge from geometry and explain all those properties that we know from those other subfields of physics. It is instructive to go back to Einstein's early work on the unified field theory from the vantage point of string theory. The key to Einstein's genius was that he was able to isolate the key symmetries of the universe that unify the laws of nature. The symmetry that unifies space and time is the Lorentz transformation, or rotations in 4 dimensions. The symmetry behind gravity is general covariance or arbitrary coordinate transformations of space-time. However, on Einstein's third try at a great unifying theory, he failed, mainly because he lacked the symmetry that would unite gravity and light. So Einstein, during his lifetime, was very much trying to unify and very much trying to work on grand unified theory. And so, but when he was alive, of course, he only knew what we knew back then, and he didn't have all the information that now, later on, the superstring theorists had and could work with, right? Yeah. You could go back to my lives from that time and watch all of it go down. I really did do that. Yes, I mean, it's live. Under the live tab. And the day after that, I went to the bakery, and that's how that whole thing went down as well. Yeah. So, yes, indeed, you could go to the live tab, my live tab on the channel, and look at the lives from that time. It will also cover a lot of these topics. In my sadness, I worked very hard at that time. I love your stream, so Indri. Oh, thank you, Steven. Thank you. Thank you, thank you, thank you. I'll keep going for a little bit longer, okay, guys? I just want to cover a little bit more about the string theory stuff. And then, excuse me. And then I want to find a different reference that I can share with you. If she's freaking out, I have to see it. Yes! You should go see it. Just search. I think I called it Election Night or something. I think that's when I started to do face lives. That was the night. In despair, I showed my face. I was like, oh my God, I've shown enough emotion. Now I have to show my face too. Remember, because I used to not actually be on the... I used to not really be on the... on the camera. I used to be a voice. So I used to just be a voice. And then on election night, I showed my face because everybody was so cozy and chatting. So on Einstein's third try at a great unifying theory, he failed, mainly because he lacked the symmetry that would unite gravity and light. He, of course, was acutely aware that he lacked a fundamental principle that would guide him through the thicket of tensor calculus. He once wrote, "I believe that in order to make real progress, one must again ferret out some general principle from nature." But that is precisely what the superstring provides. The symmetry underlying the superstring is called supersymmetry. So it's called supersymmetry or SUSY, a strange and beautiful symmetry that unifies matter with forces. As mentioned earlier, subatomic particles have a property called spin, acting as if they were spinning tops. The electron, proton, neutron, and quarks that make up the matter in the universes all have spin 1/2, and they're called fermions, named after Enrico Fermi, who explored the properties of particles with half-integral spin. The quanta of forces, however, are based on electromagnetism with spin 1 and gravitation with spin 2. Notice that they have integral spin and are called bosons. So I mentioned in the particle family called bosons, and those things have integral spin. Oh wow, happy birthday. The key point is that in general, matter is made of fermions with half integral spin, while forces are made of bosons with integral spin. Supersymmetry unifies fermions and bosons. This is the essential point that supersymmetry allows for unification, which Einstein wished for. In fact, supersymmetry allows for a new type of geometry that has even surprised the mathematicians, called superspace, which makes possible supermarble. In this new approach, we must generalize the old dimensions of space and time to include new fermionic dimensions, which then allows us to create a superforce out of which, okay, I got a text, out of which all forces originated at the instant of creation. 1 second, let me put this on do not disturb. What does spin 1/2 mean? So we can, it's a property of quantum particles. It's a property of quantum particles, and when we discuss quantum mechanics, we can go over it. But it's sort of like, you know how charge is a property of particles. Spin is also a property of particles in quantum mechanics. Okay. Some physicists have speculated that one must generalize Einstein's original principle of general covariance to read the equations of physics must be supercovariant, that is, maintain the same form after a supercovariant transformation. So you already saw my live and came back. Now, you need to watch the whole thing. You need to watch the whole thing. I don't have to suffer. Her cackle is fine. What do you have against her laugh? Superstring theory allows us to reanalyze Einstein's old work on the unified field theory, but in an entirely new light. When we begin to analyze the solutions to the superstring equations, we encounter many of the bizarre spaces that Einstein pioneered back in the 1920s and 1930s. As we saw earlier, he was working with generalizations of Riemannian space, which today can correspond to some spaces found in string theory. Einstein was looking at these bizarre spaces one after the other in agonizing fashion, including complex spaces, spaces with torsion, but he got lost because he lacked any guiding physical principle or picture to lead him out of the tangle of mathematics. But is supersymmetry the symmetry that eluded Einstein for the last 3 decades of his life? So it's kind of sad that Einstein was working on the grand unified theory for the last 3 decades of his life, and it did not lead to a successful grand unified theory. So the key to Einstein's unified field theory is that it was to be made of pure marble, that is pure geometry. The ugly wood that infested his original relativity theory was to be absorbed into geometry. Supersymmetry might hold the key to the theory of pure marble. In this theory, one can introduce something called superspace, in which space itself becomes supersymmetrized. In other words, there is the possibility that the final unified field theory will be made of supermarble out of a super geometry. So as you can kind of see, there's a lot of the geometry talk in super string theory. Basically, the reason for however many dimensions that they have is because the number of dimensions and the math that they do with those dimensions is extremely important. It's the main thing of the theory. And it's sort of all mathematics and using the mathematics to capture what they know currently and giving sort of a generalized view of things like electron, like what they said, like all the different particles are just a type of string or a string on a different octave, and the string exists in those 10 dimensions. It's basically like you could make things live in more dimensions and do the math that way and do it exactly in a way that then explains the things that we see in sort of some sort of way. Now, of course, the people who are not string theorists will struggle with the fact that your math has 10 dimensions and understanding and following that through is going to be difficult. And also, it's never going to be experimentally proved because we don't live in 10 or 11 dimensions. So these are sort of the challenges, and I would say this is what has held things kind of back. But because people asked about superstring theory, we will cover it a little bit more next time as well. I have to get going at this time, but thank you so much for joining. Always good to see everybody. And I need to find a few other books as well before we wrap up string theory. I think string theory is very interesting because with the discussion of string theory, we can I'm not mad about that. I have something. So with the discussion of string theory, we can cover all of this stuff that was going on at that time and try to understand the motivations, what things could be explained and what things could not be explained. And also, yeah, because we get supersymmetry, oh, good. Yay, good night. I will always have my copy of the book Cosmos by Carl Sagan. Yes. Good job. Yeah. Very good job, everybody, today. I think it's going to be delightful. I need to start my live a bit earlier tomorrow as well. But yes. I think I need to put some more thought and also find some more books on this. I think people are interested in it. I will warn you that superstring theory is very mathematical and it's very mathematical, and it's very the expectation is that everything will come out of geometry and this like supersymmetry, and it's not a very physical theory. So some people get lost in the understanding of it because it's not a very physically tangible theory. I want political talk with it. We can do it tomorrow. Let's do politics talk tomorrow. Thank you for liking the live. Can we get 20 likes? So it's not a very tangible theory. It doesn't let you touch and feel it and sort of get in with the physicalness of it. And it doesn't let you kind of have these like more physical understandings, Yes, politics or not, no matter who wins, can we get 20 likes? Exactly, can we get 20 likes? So So we will keep exploring it, but it's extremely geometry filled, it's extremely mathematical. Everything has a mathematical and geometry explanation in superstring theory, in string theory. So if you like that sort of stuff, we can definitely talk about it more, but it doesn't give you more physically grounded explanations. But yeah, thank you so much, everybody. Thank you for being here, and see you tomorrow. Bye bye. Yay. Bye.